Our analysis and some of our data, and that there was some added some analysis. So they consider it as pseudo-random testing. And they have an expression for pseudo-random testing, which looks like this. It looks a little complicated, but the derivation is given in their paper, so we are not going to look at it. And choose K. So they give this expression for pseudo-random testing. And for pseudo-random testing, the results would be rather similar, except when you are approaching 100% coverage, because with pseudo-random testing, it is guaranteed that a vector, typically it is guaranteed that a vector will not be repeated. So if you apply all possible vectors to pseudo-random testing, then you would have applied all possible vectors, whereas in truly random testing, it is possible that some of the vectors could get repeated. But anyway, so one important observation here is that, which is a very important observation, is that when at higher end of testing, after you have done some testing, faults with high detectability have been removed. They have already been found. If it is software, that means they have been removed, because in software you remove the faults as you find them. In hardware, you basically keep testing. So the real challenge lies in testing hard to test faults. Now in software, there was some data given by Adams, who worked for IBM. And, I was going to look up some details of this data and I forgot to do that. But basically, his data, if you would plot on a scale, there's detection rate. He looked at some large software, and he found and looked at a specific product, and looked at different pieces of that software, and he found, he looked at the defects, so defects with detection rate. So if you plot his data, so here's the detection rate, and detection rate here it is 0.017, and here it is 52.63. So it's actually a difference of about 4 orders of magnitude. And he found that things were like this. In other words, in software, you have a large number of faults with very low detectability, and very few faults with high detectability. Does this sound reasonable? Why? What would be the justification?
I don't know, it just sounds like it'd be, just sounds right.
Well, there's an explanation, and here's the explanation. At the beginning, we don't know, when the software is created, we don't know how the faults are distributed in terms of detectability. However, at any point in time, a software would have gone through some kind of testing. So for example, you do some software, you might inspect it. The inspection is a kind of testing, right? And so you might inspect it, and you might find some fault, and then do some more testing, do some more testing. So typically in software, it is tested at many different stages. So at a given, typically, when you're looking at some time in between, a software would already have undergone some testing. So if a software has already undergone some testing, then regardless of how the distribution was initially, after some testing, faults with high detectability would be very few. And the faults remaining would be the ones with low detectability. That means the ones that are hard to find. So it doesn't matter how you start. So it is possible that in the beginning, maybe things are kind of more uniformly distributed. Nobody has studied that, but I suppose you could assume. So, so if you would plot some data, let us say that here is your detectability profile, and here you have a number of high detectability faults, and here you have the low detectability faults. Let us assume that maybe at some point in time, maybe they were about equal, and then you do some testing.
Is this graph in software or hardware?
Pardon me?
This one in software or hardware or both? This one applies to software or hardware? Like based on the actual study.
This is actual data.
I mean, was it applied on hardware or software?
This was for software.
Okay.
Oh, yeah, that's a good question. Adam's data. And it is for software. Yeah, I guess I should have mentioned that. So, detectability profile is applicable to both, but in software, typically, you keep on removing defects as you find them. And although in hardware, the process is typically, you apply all of them and then make a decision.
But like at the point where we have detection rate of 52.63, then it goes like, it becomes like...
Yeah, it is actually not detection probability, but it is some detection rate in terms of some time, detection rate per unit time. So this is not exactly in the same terms as we have, and I'm not sure. I was going to look up what was the unit time, and I forgot to do that before coming here.
Yeah.
But it is per unit time, and I forget what is the unit of time in his data. But the idea is the same. These are the low detectability faults, and these are the high detectability faults.
So the vertical axis is number of defects?
Yeah, vertical axis is the number of defects that belong to that category. So this is the number of faults that have this detectability, and this is the number of faults that have this detectability. So let us say that maybe they are about the same, and you apply some testing, things would be like this. Things would be like this. So here, a lot of faults are going to be found and removed, and here the number of faults found and removed will be small, and more like this. And eventually, what will happen is things could be like this. So the low-hanging fruits are all gone, they've all been picked. And of course, the hardest one, the faults are here. Did any of you live near a garden where there were fruit trees? So when I was little, so there were a lot of fruit trees, and we would go there. So all the fruits that we can reach are they're gone, and once on the top where you have to climb up or throw rocks, and that used to be dangerous, but we used to do that. So those are the ones that would remain. So it's the same principle. Now there's a saying that I think somebody wrote a book, everything I learned in kindergarten. Has anyone come across that book? So a lot of stuff I learned when I was little. And everything is more or less the same idea, right? So, except I throw some mathematics at it. So, okay, what is the implication? Now it has actually significant implications. One of the implications is, now how many have you heard about false seeding? Okay, so false seeding is an approach where objective is to estimate the number of faults in the software. And the process is that, okay, I guess I will keep this equation. And objective is, yes, to estimate the number of defects that are in some software. So you have the software with some defects. So you insert some defects in it. And let us say you have inserted 20 defects. And you test it. And you find, let's assume you inserted seeded 20 faults. I'm just constructing an example. And then you did some testing. And let us say you found 10 seeded faults. And you found 5 other original faults.
Can I ask? I have a question about the previous diagram, please. Yes.
Okay.
So we have 3 curves. So what does, like, how they differ with the 3 curves that you have?
Oh, these curves here?
Yeah.
Oh, this is in time to time. So here is some testing. And then more testing. By testing, I mean testing and debugging. So you have you say some and some more testing and debugging, and more testing and debugging. So as you keep on doing that, the more and more, the faults that tend to remain are the ones that are hardest to find. That's the idea. Okay. So you want to find out how many faults are in there. You seeded 20 faults, and then you tested, and you found 10 of the seeded faults and 5 of the original faults. Then, what can you say about the original number of faults? What would be your estimate? Notice that you found a half of the seeded faults, right? And if you assume that your seeded faults are representative of the kind of faults that are in there, then that would mean you have found half of the original faults. So the original number of faults must have been 10. This is a popular way of estimating the number of faults in a software. So it works this way. Let me put it in some algebra.
So basically we just found 10 faults. So how do we get the number 5?
Let us assume that we seeded 20 faults in some software. And then we did some testing. And as a result of testing, we found some faults. And these faults found, so we found 15 faults. And 10 of them are the faults we seeded. Now the faults we seeded, we know which they are, right? So we can identify them. And then we found 5 other faults that we did not seed. So originally it had some faults. And that is our objective. We want to estimate what was the original number of defects. So here, you can estimate that, okay, you found your testing method, whatever that was, found half of the seeded faults. So you could assume you have found half of the original faults. So original number of faults must have been 10, right? So here's, let me put this algebra, put this logic into a little algebra. Okay, the program has X defects. And we want to estimate X. So this is the unknown we want to get. So here we seed J new faults. And then do some testing,